Nous pouvons commencer?
Oui, monsieur.
Well, with great pleasure, I'd like to introduce one of our distinguished, relatively new faculty members to Berkeley, Alexandre Bayen. Today has been an extremely exciting day for the university because in conjunction with Nokia and together with many of our transportation officials, they've been running this really spectacular experiment using Nokia phones and information to guide traffic through this special course in the South Bay. And so the Citrus seminar feels very honored to host Alex. I want to emphasize that this is being broadcast to the other 3 Citrus campuses, so this is a California-wide event for this very important California-wide moment. And in the traditional way, I'd like us all to welcome Alex to the stand with a round of applause. Thanks for coming today.
Thank you all very much for coming. I'm really, really excited to be here, and I'm especially even more excited to show all what we've been doing today. And so in the spirit of what is called the Friday Transportation Seminar, I would be tempted to really go on and on and on about all what we've been doing today and show you spectacular pictures. But at the request of the ITS director, Michael Cassidy, I really want to also go a little bit in the details of the math that are behind this technology, which we're going to show to you today. So I'm with the Systems Engineering program in the Civil and Environmental Engineering department. And today I'm going to talk about Mobile Century, which is the name of the experiment we're running as we speak now, that is focused on monitoring highway traffic using N95 Nokia cellular phones such as this one. So I'm going to start with numbers which I think are very compelling when it comes to traffic. In fact, if you look up there, the 4.2 billion hours extra travel in the US and 2.9 billion of gallons of fuel which are used to do this, and the congestion cost, clearly we all know, especially in California, that traffic is a big problem. And now, as users, when we hit the road, it is very important for some of us to really understand what are our options in negotiating commute better. And if you live in the Bay, you can call 511. You can go to 511.org if you're at a computer. If you're traveling on a highway which is instrumented, you can look at the changeable message signs. So there's other phone services. But as we all know, not all roads are covered, and traffic increasing and increasing more and more as time prevails. This will not be enough to cover all the congested roads and provide all the services we need. And this is really the motivation for the talk today. Additionally, for people who are in the business of planning, tools like PEMS, the performance measuring system that has been developed at Berkeley, also enables very efficient solutions to archive data and do studies that help California, or more generally transportation agencies, to develop the transportation system and make it a more efficient system. Now, what you have to know about this system is that today, when you log into 511.org, or if you look at traffic.com, most of the data that you see displayed comes from sensing technology that is relatively traditional. In fact, if you've driven on the California highways, you will certainly have seen these loop detectors in the pavement, and this is really the most traditional way of sensing. This would be kind of the next generation, which is now wireless. Some specific places have also solution-specific solutions like cameras. And if you're lucky to live in the Bay Area or some places on the East Coast, fast-track transponders or easy-pass transponders are also used as a mean to produce consumer products such as travel time. The problem with this is, A, it is expensive. I mean, if you're an agency in your business of deploying these, you know that this is really expensive. B, it costs money to maintain. C, the reliability of such technology is not always obvious. And simply, a lot of places are not equipped. If you don't live in a place where there's toll tag readers, you just don't have this as a sensing mechanism to provide that data. And so this is where this guy comes in the picture. The experiment which we're showing today uses N95 cellular phones, such as the one which is shown here, as a way to gather data and use that data to provide the same level of service as you have on a website such as 511.org. So what you see here that was shown today is basically a velocity contour of I-880 southbound and northbound. And the data that you see currently broadcasted on this screen here is collected from cellular phones only. So for example, if I read 51 miles an hour here, it means the local velocity of the highway is 51 miles an hour. You can also see these numbers here, which are travel times, and these are travel times that we can compute from these velocity reconstruction. So the contribution that I'd like to talk about today is the algorithmic work that goes behind the scenes when, from these distributed measurements, how does one go about reconstructing such an information. And again, focusing on the cell phone for a minute, if you think about a modern cell phone, at the age of convergence of communication, sensing, and multimedia, now in such a device you have everything. You have a GPS, you have an MP3 movie player, you have multiple sensor accelerometers, radio, wireless, Bluetooth, infrared, and you even have a 5-megapixel camera. So this device is really the device that will be used in the future to track mobility, and our specific application for today is traffic. So this brings me straight into the outline of this talk. And the first thing I'd like to talk about, and really in the spirit of the Friday seminar that is happening today, is talk a little bit about the mathematical models that go behind the scenes. Then I'm going to talk about a very, very, very important topic of today, which is privacy. Obviously, it's very cool to track people with phones, but if you think about it, it's maybe not such a great thing. So if you do it, you should do it properly in a way that you do not intrude people's privacy. And then I couldn't resist the temptation of showing you some of the pictures of what happened today on the highway, because I think it was really the work of a fantastic team. We currently have 165 drivers on the field driving 100 cars with a staff of 40 people monitoring them. So it's really a large-scale operation, and I'd like to spend the last couple of minutes of this talk to talk about the operation. So going to the sensing, this is what this phone can do today. This N95 Nokia phone is capable of positioning the owner of the phone anywhere where the phone goes. So this is where my student Juan Carlos Herrera lives. Okay, so much for privacy. And so this is an example of a trial run that he did a couple months ago when we started this experiment, in which he basically drove home, picked up something, and then went straight onto I-80. If you know Berkeley a little bit, you will recognize this is close to the marina, and took a couple runs around to just test the GPS sensing capabilities of the phone. And so looking at these results, and obviously the key point here is not so much the geolocalization capabilities of the phones as much as the capability of transmitting this in real time to a central system, which is really what we're talking about. This convinced us that this was really the right technology to pursue further. And it's interesting because historically when we started working on this, there was a lot of skepticism about the accuracy of such tracking device. And the reason is most of the studies done in the field use triangulation. Triangulation is very bad in terms of accuracy. GPS really puts us at 1 or 2 levels above in terms of accuracy. And so if you look at this plot here, this is time, and this is the velocity of the car. This guy driving the car was my other student, Dan Work. And you can see the speed recorded by the speedometer in red, and then you can see the speed recorded, ignore the green for now, by the phone in blue. And quite honestly, when I see the car driving nominally something like 58 or 61 miles an hour, I have more faith in my cell phone than in my speedometer. So based on this, what we're doing today is an experiment in which we are going to gather this data and use this data to reconstruct flow, field, and velocities on the highway, as well as travel times. So the site on which the drivers are deployed today is at Union Landing. That's in Union City. And to give you an idea of some of the preliminary runs we did, each time, and this is going to come over and again during this presentation, our visualization tool basically plots velocity as bars. So for example, a bar of 59 means this record of the driver driving right here is 59 miles an hour. That's southbound. Green means the guy was going kind of fast. And when you see like short bars in red, like 18 means the guy was going northbound 18 miles an hour. And the red indicates the guy is going slow. So the color code is pretty much the same as the one you will see here. And this is going to be a convention we use throughout the talk. OK, so now going to the first order flow models which are used for this study. The key thing we do here is it's good to measure things, but if you don't have a good model of traffic, then your measurements might not be very helpful. And so this is exactly the business in which we are in systems engineering, is providing algorithms that enable to blend a very nice technology and a very nice application such as traffic engineering. So this is kind of transportation 101 for people who have taken any transportation class here in this university. This is kind of easy, but I'm just going to go through this one time because it will be one of the main fundamental frameworks that we use here. So when you model traffic, a very useful quantity that you'd like to see is density, which we called rho. And density in everybody's language is really the number of cars per unit of space. Okay, so we call this rho. Obviously, it depends on x, space. Okay, my density of cars is not the same here and 2 miles ahead. And on time, as we know, traffic builds up and clears away. So the evolution of density on the highway can be modeled very simply by first-order hyperbolic PDE, which goes back to the 50s. It's called the LWR PDE, which reads like this. And what that equation means is basically that the rate of change of the density locally is equal to a mass balance of whatever is coming in minus whatever is going out of that small control volume. So even if partial differential equations are not something you eat every morning for breakfast, that very simple equation here basically encodes the conservation of flows of vehicles on the highways. So the idea behind building a system like this consists in taking measurements from the phone, plugging it into this mathematical model, and then making an estimate of what that state is, rho. And you all know, if you have ever looked at 511.org, that when you look at the color code, when it says black, congested, it basically means very high density, and that's what you would like to avoid. This is exactly what we're computing here. Now, you might wonder what that function Q is, and that function Q is called a fundamental diagram. And a fundamental diagram is a diagram that relates the density, or occupancy for the present plot, that's the number of cars per space unit, to the flow of cars, which is the number of cars that go through a reference point at a given time. And that curve here is relatively straightforward to understand. Low density, low flux, okay, not many people on the highway, and the more people, the more flux, and at some point there's a maximum, and then if you put more people on the highway, then the flux decreases again because traffic jams start to happen. Okay, so this fundamental low that appears in the PDE right there has a very good physical interpretation that you can relate to, because if you are moving in free flow, basically you're in that region, and if you are in very high and packed density regions, then you're in that region and the flow of cars is relatively low. So when you look at a display like 511.org, basically you look at colors, and the colors can encode two things. They can encode density, and sometimes it's not always specified, so you don't really know what you're looking at if you're looking at density or speeds. But when you look at densities, green will encode low density, and yellow will encode higher densities, and red will encode even higher density, and so on. So what we're talking today is basically mathematical algorithms that compute these density from these measurements. And if you think even one step further and you'd like to talk about a product, then the output would be the color maps on this map here. Now, you might be interested in density, but in fact, as a driver, do you really care that you're in an area where there's 1,000 cars per mile? Not really. What you really care about is speed. And so the beauty about the mathematical representation of this problem is that there is a cousin equation of that PDE, that I showed before, this partial differential equation, which is written up there, and which is very similar to the evolution of density, except the mathematical model behind it represents the evolution of speed. So in everyday's word, what that means is that you can also mathematically compute the evolution of speeds on the highway in a manner very similar to the way you would compute density. And similarly, you would compute a color plot that you could broadcast on the web that would say, okay, green means like I'm going 65 miles an hour, red means I'm going 10 miles an hour, and so on. Obviously, these are two important things that are interesting to convey to commuters. Now, from a traffic perspective, there's an additional quantity that is also of interest, and that's the accumulated vehicle number. So if you think about density, well, maybe what you really care about is the total number of cars on the highway, because for some transportation agencies, that's helpful. So you really care about the total number of cars on this green strip here. Now, the interesting mathematical feature of this, without going into too much detail, is that that number, which we can call n, which n for number, is the total number of cars between a reference point and any other point, is governed by an equation that is also known to us, and that's the Hamilton-Jacobi equation, which I'm writing here. So again, if the Hamilton-Jacobi equation is not something that you're familiar with, the good thing to remember here is that this equation has been studied heavily, almost to death, for 150 years. So once you have shown that the quantity of interest can be cast in that format, you can use a lot of good tools to solve this equation. And finally, and that's very important for privacy, there is a fourth quantity that might be of interest for the transportation engineering community, and that's vehicle label. So imagine I'm a vehicle, and I'm driving through the highway, and I'm interested to figure out where am I, or someone, let's say the monitoring agency, is interested in figuring out where am I a couple of minutes later. So by the time I cross this line, I'm going to be assigned a label. For example, I'm the 17th vehicle of the day to cross that line. What I would be interested to know is 5 minutes later, where is my vehicle number 17? So somewhere around there here. Well, interestingly, the evolution equation for that label function, which is called M is named after Moskowitz. In fact, Professor Carlos de Ganzo in this university was one of the first people to formalize this. Well, this equation for M is also a Hamilton-Jacobi equation. So in mathematical terms, that's also an animal that we can deal with. So that brings me to my sensor menu today. Going back to this technology I described earlier, we have a lot of sensors available here. And going back to these pictures that I showed before, if I try to do a map of where the sensors can be helpful, if I'm interested in densities of cars, then loop detector is a really good way of measuring this. If I'm interested in cumulated number of vehicles, loop detectors are also a good way of measuring this because they count cars. Now, if I'm interested in velocity, cell phone or GPS or cameras are better because they have a much more accurate estimate of velocity. Loop detectors can also do a good job, but usually the quality of the data you get from them is not as good. If you're interested in vehicle labels, then you really need to track the vehicles, and so then loop detectors are not an option anymore. You really need to use cell phones or cameras. Now, our product today is travel time. Now, all of these, whether you're interested in density, in velocity, in labels, or number of vehicles, all of these can be used to compute travel time. And so what I'm going to show first is, well, for these travel times that you can see in real time from the system, what are the techniques we used? And more importantly, looking at the future, if you want to get more information without intruding privacy, which of these frameworks would you use to do this? So that brings me of what we're seeing today. Today, we're looking at a velocity field reconstruction from these mobile sensors. And the particular technique, so that's why I've put a green box here. We're interested in velocity. And that would be the color map here. And then we're interested at travel time. That's this green box here. And they would correspond to these boxes here. So here, we're looking at a 9-minute commute time from Decoto to Tennyson Road if you're going northbound. So how did we do this? How do we basically broadcast this data in real time? Well, what we do is we take our first order hyperbolic PD for speed, okay, because speed is what we're interested in. So you can skip these mathematical details here. They're not important. I'm just putting this for completeness. But basically, we take the speed evolution equation. We discretize it. Again, this is kind of numerical analysis 101. That means we take this continuous equation and we make it into a discrete system. And then we solve a Kalman filtering problem on this set of equations. And so I have summarized very briefly what an ensemble Kalman filtering algorithm does. But in a nutshell, basically what we do is we gather data at specific points, and then we compute the best possible estimate given that the model equation is nonlinear and is in discrete time. So what I really want to touch base on today is privacy. In a sense, reconstructing velocity field as we're doing here, I don't want to say it's straightforward. I mean, we basically have a very large team working on it, and it's not been done this way before. But I think the challenging part of this research is privacy. We are at the age at which we can monitor your position on the highway every 3 seconds with this device. So the main question we'd like to answer is how do we do it, A, in a way that does not degrade the quality of information in order to provide that service, but B, how do we do it without invading your privacy? And so the main scientific question that goes behind this is how do we incorporate Lagrangian measurements, which is another way of saying mobile measurements. How do we incorporate Lagrangian measurements in estimation algorithms for traffic? So that brings me, again, to my sensor menu. But this time, what I'm going to be interested in is vehicle labels. Okay? I'm tracking cars on the highway, so potentially if I could track everybody, I would have the possibility of following the labels all the way through the highway. So I'm going to focus now on the equation that I can use in order to track labels on the highway and see how that equation can be used to compute travel times. So just a reminder of the thing I've shown you before. The equation I'm going to solve now in front of you is this Hamilton-Jacobi equation in which the main variable I'm dealing with is m, and the function m is a function which encodes the label of the car traveling on the highway. So this will make control theorists happy. It's an interesting situation in which we have a transportation engineering problem, in which we have a model equation which is really given to us from the flow dynamics, but the method that we're going to use to solve it is a control theory method. So what I'm plotting on this axis, x for space, t for time, and m for label, is basically a curve which increases with t. So I'm standing at a reference point. There's cars driving by, and as the cars drive by, I assign them a label. So first car gets label 1, second car gets label 2, and so on. So clearly that function has got to be increasing. And then if I look at t equals 0, my initial conditions are such that, well, the cars that drove there first and are the furthest away have low labels, and the car that just passed me have higher labels. So I also have a function which, if you look at it this way, would be decreasing. So this is the 5 minutes of control theory in this talk. Now what I'm going to do in control theory terms is I'm going to create what I call a target. And in mathematical terms, a target is basically a subset of that space to which I would like to go using a specific equation which is called dynamical system. So I'm looking at what is called mathematically the epigraph of this curve. That's this green set above the curve. And I'm going to consider this as a target for my problem. Now I consider a point in this space, so time, space, and label. And I'm going to ask myself the very simple question, if I'm standing there, can I reach my target? So now we totally forget about traffic. Okay, this has nothing to do with traffic anymore for the next 2 minutes. This is pure control theory. But I'm asking myself, how can I reach the target from any point? And you can see that if I start too low, because my trajectories are going down, I'm going to miss the target. But if I start high enough, at some point my trajectory is going to meet the target. Okay, that means I can reach the target. And so what you can physically see, even if you have never seen these equations before, is there is some kind of a lower limit above which you can reach the target and below which you cannot reach the target. So it's a kind of a, mathematically speaking, is a kind of a surface that defines this boundary. Well, it turns out this surface is actually the surface that describes the evolution of labels on the highway. So I have used some control theory algorithm which might seem obscure, which we can now forget for the rest of the talk. But what that algorithm does is it produces a surface. And if I read at a time t equals 17 and a location x equals 3, a labels equals 23, that means vehicle number 23 at time 17 is at location 3 or whatever I said here. Okay? So now we forget all the math behind it. We just remind ourselves what is the surface. The surface is the evolution surface of the labels of the vehicle. So logically, an isoline of that surface is a line of constant label. That's a trajectory of a car. So if I pick an isoline of value 17, well, that's the trajectory of vehicle number 17. Now, how does this relate to the cell phone problem? Well, the cell phone is capable to tell you every 3 seconds where you are on that trajectory. So this brings us back into the tracking problem. And why is that? So this is an example of a label function. So this is time, and this is distance, and this would be the corresponding stretch of the highway. So each of these trajectories here is basically a trajectory of a single vehicle undergoing this travel on the highway. And you can see on this plot a lot of interesting things. If I look at this trajectory, so it's like a car starting from here and driving there, you can see at some point there is some kind of a little dent here. That means during that period of time, the vehicle actually slowed down a little bit. You can see this dent here. And you can see this kind of shockwave effect behind due to the slowing down of the vehicle. Now, why the vehicle slowed down, I don't know. But it's certainly not in the model. That's not predicted by the model. Maybe the guy got a phone call. Maybe there was something cool on the radio. Maybe there was a fire truck driving the other direction. He got scared. For some external reason, which is not in the model, this guy slowed down, and that created a back-propagating shock wave on the island. By the way, this is real data. This is from the NGSIM data set. That's the data set that we have at Berkeley that is extracted from video data. So we know this as the ground truth for this very short stretch of highway. And this is where the cell phone becomes very helpful, because maybe you can measure things here with loop detectors. Maybe you can measure things there with the loop detectors, but you certainly cannot measure anything here unless you have a cell phone in your car. So the question is, going back to my surface analogy, how do I incorporate this in the model? And what that means in mathematical terms is if I go back to my isoline of value 17, so the trajectory of my car number 17, well, what that cell phone information tells me is right around there, you're not where you think you were because something happened. Now, if you know it from the cell phone, you can put it back into the mathematical equation. And the algorithm that we have developed to do this over the last couple of months basically enables you to incorporate that information inside that surface. And anybody who has dealt with partial differential equations in this room knows that it's easy to solve partial differential equations when you know values at the boundaries of the domain. But it's very hard to do when you also prescribe values inside the domain. And this is exactly what we're doing. So in mathematical terms, what we're doing is we're developing a theory which enables you to add information inside the domain. And the difficulty of incorporating that information does not satisfy your model. And again, the reason why it doesn't satisfy your model is your model doesn't predict that your wife would call you at that time and that because your wife called you, you slowed down. So bringing this to a higher level of mathematical description, what we're really dealing with here is a problem in which we have now three types of knowledge. We have what is called boundary conditions. So that would be the red line here and the black line there. And this could be loop detectors. Okay? You're putting some loop detectors in the pavement. They count cars. They can eventually measure velocities. So as cars drive by, you can measure the flow here and there. Then there's initial conditions. You can always assume you knew the conditions in the morning or in the middle of the night. It doesn't really matter because in the long term they're going to be flushed anyway. So you can assume you know this. And the novelty today is, well, now we also have the possibility of integrating data here inside the domain. And solving partial differential equations with this type of data is not trivial. So now there's a lot of issues that go with it. Well, the first issue is, like, from a transportation engineering perspective, clearly what you would like is you would like to know every possible thing about every possible car all the time. And that's very privacy intrusive. So the goal of the tools that we're mathematically building here is to find the proper interface between privacy and accuracy. So from a privacy perspective, the less you give, the better off you are. From a transportation engineering perspective, the more you have, the better you are. So where we are operating is at the location where it could be a little bit of both. And if we're able to ever define a place where you can guarantee that you have a form of optimality between privacy and between accuracy, then you're really in the sweet spot, and this is what we're after. Now, in the current system that you see today, we have dealt with this at a system level. So today, while the experiment is running, just to guarantee that we are operating in a privacy-preserving environment, we use data anonymization on the phones. That means anything that leaves the phone does not have your number or your name on it. We use up to the state-of-the-art cryptography techniques, so same encryption techniques as you would use, as would be used by banks or other companies. And also, we have a very specific way of doing mobility tracking. We do not need to know your information everywhere. So in fact, if you look at this, you really only need a couple points. Because once you have this, the model will do the rest for you. And so part of the way we do this is by making sure that we don't just collect blindly data, because if you are very careful about where you collect the data, most likely you will have all you need to reconstruct the traffic accurately. And the key concept introduced today, well, obviously they've been working on, for this on a long time, is the concept of virtual tripline. So, Nokia, and I'm going to talk about this towards the end of the talk. I think that one of the key contributions of Nokia in this experiment is they have introduced this form of virtual loop detectors, which they call virtual tripline, which, as we will see, is a way of doing detection without invading privacy. So now, going back to my problem, I'm going to show the mathematical methods that we're developing to quantify the intrusion of privacy, the intrusion of accuracy on privacy. So in other words, obviously we have not solved that problem yet, because otherwise I'd be a very happy person. We're just at the edge of defining mathematically what are the techniques that can be used to quantify, how much is my privacy going to suffer if I want a little bit more accuracy. So I'm going back to my 0.4 mile stretch of highway, and still using the same ngSim data set. And now this time I'm interested in the cumulative number of vehicle function I said before. So in other words, I'm interested in computing the cumulative number of vehicles between this entry point and any arbitrary point here. So let's first imagine I'm only using one loop detector. Okay? So loop detector, you put it right there. It will count all the cars coming into the system. You can relatively easily conceive that the further you're away from the loop detector, the less you will know about traffic, because people call each other on cell phones, people don't obey physical models. So basically, the information that you have here might be very high quality, but the further away from the detector, the less you know. And this is exactly what this plot shows. So here we're showing about 140 seconds of error. And what that error encodes is the difference between the ground truth, how many vehicles on that stretch of highway, and what you think, using that detector, that number is. So if I look at a point here, it's black, it says 5. That means I'm off by 5 vehicles. If I look at a point here, it says 30, then I'm off by 30 vehicles. And the interpretation of that graphic is very intuitive. If you're close from the loop detector, well, you're relatively black. And that means basically the quality of the information you have is good. You have a relatively small error here. And the further away downstream, the worse it is. And it makes sense. If you're 0.5 miles away from the detector, maybe whatever the detector says doesn't really make sense anymore. So now let's see what would happen if you had a second detector. Now you had a second detector here. Suddenly you have found yourself, you've reduced the error downstream. And it makes sense again. Because even though traffic is going this way, having a detector here tells you also about the conditions of traffic upstream. OK, so here I have not intruded privacy anymore. All I have done is I have put 2 loop detectors in the pavement. So now let me add 1 point. So imagine I could track one guy one time. So I select a guy, random, and at some point, at some location in time, I'll decide, I know that's you, and I know where you are. Is that really privacy intruding? I don't know. This is not really me to decide this. I'm not an expert on privacy. But what I can tell is, as a traffic engineering person, this is how much it reduces my error. And you can see, in the direct vicinity of that point, we have a lot of black area here. And that's good. So this is how much value you get for one GPS track. Second GPS track, third GPS track, and so on. So you can see it's not too difficult to make that whole picture black. And so, in other words, the frontier at which you need to operate to have good accuracy is maybe not that privacy intrusive. We don't know it yet, and we don't know how to do it, but we have the proper mathematical tool to quantify it. Now, you want to be a little bit more privacy intrusive? Well, OK, let's try to follow one guy for a couple of seconds. So now let's see, we follow this person. OK, so this is the time, and this is the position. And let's see what that does to our error plot. If you can follow the person for a little bit of time, then you have a lot of black around here. OK, so clearly, you have improved your local measurement and prediction much better. Follow 2 people, follow 3 people, and clearly, you've made this very black again. So really, what I'm trying to convey here is that the trade-offs between privacy and between accuracy are hard to define, but these simple computations realized with real data, and this is still using the Anderson data set, give us great hope that we're not too far from being able to create a privacy-preserving environment that can monitor traffic extremely accurately in real time. And for this, Nokia has introduced an additional concept, which I want to describe in the next couple of minutes of this talk, which they call virtual trip lines, VTLs. So virtual trip lines are, if you will, virtual markers that can be deployed virtually on highways to detect when cars drive by. So if you look at this plot, which I've shown initially, you can see these red lines on the picture here. Okay? This is typically a virtual trip line. And so that virtual trip line is a total virtual object. But what it will do in the system, and this is the way the current system is working today, is it will send an update as the vehicles or some vehicles drive by. And what Rutgers University, which is one of our partners for the study, has shown is that if you operate in these environments, then you already solve a lot of the privacy problems that arise when you start tracking people with cell phones. So in order to kind of showcase this, what we did is we first ran a first field experiment, and that was on November 2nd of last year, in which we ran 20 cars. So you could just see this car leaving the Palo Alto Research Lab, crossing the Dumbarton Bridge, and going onto the site to kind of test the way this VTL business will operate. And so the site at which we're operating today, which is this site, and that's the Union Landing Retail Center, is our base station. And in the video that I'm showing here, which is from our test on November 2nd, basically what we did is we started launching cars back and forth, running here to test our VTL server. So basically, each car of these 20 vehicle test pilot deployment we did was carrying one of these N95 phones and sending us updates as they drove by. So here, for visualization purposes, I've shown the whole trajectory with all the updates. But as we were operating to test the system, we were only sending data where a VTL was deployed. And this is a display from the dashboard of my student Dan Work's car carrying the N95 as he was running the experiment in November. And just to give you a visual illustration of how this environment preserves privacy, so in the previous transparent, you've seen this kind of car moving up and down and up and down and up and down. And if you follow the dots, you can really follow where the car is visually. What I am showing in this movie is the data updates we get from the VTLs. And what you see visually is you see dots popping up, popping out, popping out, popping out. But even though there is some mathematics that they have been developed behind that I don't want to cover in this talk, it's very intuitive to see that this environment is a much more private environment to operate on. If I ask you, was the guy driving this way or that way? Well, I guess you have the map behind, so you know that at least in this country, you drive this way and that way, not like in Britain. Sorry, Paul. So here, what they're trying to showcase is the fact that by not being able to follow the trajectories at a rate which is too frequent, and by having a selection procedure that enables you to not disclose too much about the person driving, you're operating in a safe environment. And to give you another visual illustration of this, this would be what you would see as the cars are deployed. This is still from our November 2nd experiment. And now that several cars are turning, you can see from these VTL updates that you get in real time that it is very hard to track people individually. And again, there's a whole study that has been done at Rutgers University to show that this environment is safe. So our job as transportation engineers, and this is again in the spirit of defining this frontier between accuracy and privacy, our job in transportation engineering here, or systems engineering, is to make sure that we're able to get a good accuracy result from these degraded measurements, i.e. these measurements that are not providing values of the speed everywhere. To show you one last movie of our pilot test on November 2nd, this is what you would see, kind of a Google rendered aerial view of our vehicles, and you can see some vehicles overtaking each other. And this is the data set that we're using to do our studies here. So now going back to my screen here, this is broadcasting data live from our command center at Union Landing. And the reason why we have selected this site is there is a very known bottleneck on this location of I-880, which is right here. And in fact, you can see it's pretty severe, because if you were close enough, you would read like the guys in this zone are driving 19 miles an hour. So when we selected our site to do this first experiment, we made sure to have a bottleneck that activates every Friday, because we're going to operate on a Friday anyway, so every Friday around 2:30. And in fact, for those of you who have been here throughout the day, when you first came in this room, everything was green, and around 2 or 2:30, this portion turned red here. So now, I'm in the last couple minutes of this presentation, I would like to show you a little bit of the logistics of the experiment, and I will conclude with some comparison of what we got today out of the system versus what you would get on the web if you were using a system like 511.org or any equivalent system. So I'm going to finish off with about 10 minutes of presentation of our operation today and some of our preliminary results. And let me emphasize again, the operation is still running. It will be running for 2 hours and 10 minutes. So we currently have 100 drivers looping around and sending us data in real time through the internet. And this data is broadcasted both to the Nokia Research Center in Palo Alto and here at UC Berkeley. So in order to recreate an environment which would be somehow representative of what you will observe in real life in a couple of months, something like 18 months, we created a cycle of about 20 minutes. So if you're driving northbound and southbound, this stretch of highway is going to take you about 20 minutes, depending on congestion. And if you have 100 drivers on the road, and if you don't allow them to drive in the carpool lane and you just exclude the carpool lane, back of the envelope computation shows that the penetration rate will be somewhere between 3 and 5%. So now, as I said, at 2:30, congestion starts to occur here, and then densities will increase. As we all know, if we ever sit in traffic, car density becomes very high. So in the morning, we have operated on a stretch of about 10 miles between Winton Avenue over there and Stevenson Boulevard down there. And we basically have been operating on this route until noon. And our back of the envelope computation really show that that gives us a penetration rate of 4 or 5%, which is exactly what we're after. At noon, all the drivers switched to short loops where they start to loop between Winton Avenue and Dakota Road. And now you see different teams, and we have 3 different teams of cars to enforce commute or to enforce driving patterns that are not clustered. So if you have everybody drive the same loop, then you can get into issues where people start to pack up and the penetration rate might locally become very high and some other place very low. So in order to make sure that the penetration rate we have is good everywhere, we have in each of the scenario we have 3 teams, and each of them is driving a separate loop. And from a privacy perspective, it's also very good because it enables Nokia and our Rutgers partner to test their privacy algorithm. They can figure out, oh, can I really track this guy versus this guy? So this experiment really serves different purposes, both the flow field reconstruction, as you can see here, as well as the privacy study that our partners are doing. Just one very quick slide about the system. I think you might want to know what's going on behind the scene between this guy and the screen. So typically, you have a GPS device on the phone, and which basically collects position and velocity, which sends it to the tower, which itself sends it directly to the ID proxy server. And what that server does is it strips off your data. Okay, it doesn't. So Alex Bayen 510 whatever, my phone number gets stripped off, and it just sends a speed measurement. So this is a form of anonymization of the data that happens in this block here. Then this is sent to a VTL server, and I've just explained what a VTL is. And that VTL server is interfaced with a model server. This is where our traffic engineering expertise come in. So this is where my model goes, my PDE, my label equation. And from that model server, I can transmit it to a visualization server. Okay, so this is really a one-slide show of the system that is deployed today. And I've put a special arrow in red. Obviously, we're very worried about safety. We have 165 Berkeley students on the road today. And we want to make sure that if they're in trouble, we know where they are. So today, and only today, we have an extra feature where we can also show where all the cars are. And so if you stick around after the seminar, I can maybe call my guy in the command center, and he can probably superimpose the dots so you can see the cars moving on the map. But I don't want to do this now because I'm really interested in showing the type of service that could be provided using this type of technology. Now, what good is that data? So one key thing in trying to show that we were successful today is later on in the process to be able to show that our travel time computations were accurate and correct. And the good way to do this, or one possible way to do this, is to know the ground truth. Now, how do you know the ground truth? If you don't have cameras everywhere, one good way of doing it is to put cameras on bridges. And so today we have 3 camera crews of 9 students on bridges. So these are the 3 bridges, and which are basically filming traffic. Okay, it's a good weather, so it's hopefully a not too bad experience. And with high-res cameras, it's very easy to read the license tags. So now if you can track car ABCZB3 here at 3:03 and ABCZB3 here at 3:07, you know the travel time was 4 minutes, and that's the truth. So it is very important from a scientific perspective. I mean, it's really cool to build a system and say, okay, well, I'm able to display a color map. But it's not very helpful unless you can show later, once you do the data analysis, that, well, you were off by a couple minutes. And so these 3 teams of students that we have here are basically recording 6 hours of data so that we can later say, well, you know, we did a fairly good job in computing that travel time. Now, I'm very excited also to show you what happened this morning. This morning, we were at the Command Center on Union Landing, and I'll show you a couple pictures of that in a minute. And we started the first wave of cars at 10 o'clock. So we had these 100 cars lined up, and at 10 o'clock, we started launching cars on the highway. And then suddenly, real quick, some of these dots here started to turn yellow with 12 miles an hour, 13 miles an hour. And people in the command team and in the center started turning a bit nervous as that can be true. I mean, the highway is free flow right there in front of me. And I can see 2 miles downstream, you're telling me the system broadcasts 16 miles an hour. Now, we had NAVTech guys in the audience, so they called their friends at their command center and say, what's going on? I can see on the map that it says 13 miles an hour, but why is that? And within 2 minutes, we had captured a 5 pileup car accident. So it happened on that day that a couple minutes after we launched the experiment, there was a major accident north from where we were, and that created a shockwave. We really saw it happening in real time, and a pileup of cars. And this was almost instantaneous. So, of course, the experiment is still running. So I cannot show you quantitative validation of how good a job we did, but this is what was on 511.org today, right after the experiment, or the accident. This is what we had today. We don't use the same color code. So the red here, in terms of severity of traffic, matches the yellow here. But I think this is a very compelling case of, you know, this system is working. And in fact, at 2 o'clock, when the speakers were presenting their presentations today, I was very anxiously waiting for this bottleneck to activate. Because we've been observing that bottleneck for weeks. And we know, as I said, between 2 and 2:30, that will turn red. And we were, OK, so. Oh, no, that's OK. I have like my whole crew is actually calling me if there's anything. So as Quinn Jacobs would say, like, if this guy starts ringing and ringing, that means maybe someone is in fire. I mean, so anyway. But I just want to say this is really a compelling case why this system is working. And obviously, now that we have the video data, hopefully very soon we'll be able to provide quantitative validation of this. But you can see, and this is a bit later after the accident, now the situation turned really bad. There's black, and we all know when you look at 511.org, when it's black, it's not good. The predicted velocity on the northbound side were very bad. And in fact, now you can see these blue dots. Okay, so these are the cars. So these are our drivers. And I assume that Jeff Ban, who was in the command center where that happened, started to turn on all the vehicles because everybody was getting a little bit nervous here. This kind of gigantic pileup, so we want to check on our drivers, to see how they're doing. So in summary, I think what I've tried to convey in this seminar is at the age of convergence of multimedia sensing and communication platforms, tools such as cell phones can really play a major role. And in 18 months, most of the major cell phone carriers will have a GPS, and that means this system and these algorithms potentially can go everywhere where there's traffic. So this system is not only helpful for commuters, but it can also help you with multimodal transport. Should I switch to the BART? Should I switch to the bus? Should I switch to my bike? And it can provide a lot of different additional services based on this technology. And so now from a university perspective, what really we're interested in doing here at Berkeley is providing the right mathematical tools that will enable us to quantify the trade-offs between privacy and accuracy in order to be able to create a monitoring system that operates in a safety-preserving environment. So we're almost done, but as I said, there is a crew of 40 people just monitoring our 40 drivers. And I really want to give enthusiastic acknowledgement to my team, my students, but also the CCIT staff, the ITS staff, and all the people who have collaborated with Nokia and Rutgers to this experiment, because working with such people really enabled this amazing experiment to be feasible. And I really want to pinpoint Dan Work and Christian Claudel, who are my main two people today in the field taking care of these issues. I really also want to acknowledge all the staff of CCIT. CCIT has provided a great support, and JD is here today and has been really instrumental in getting this project started and helping us to create a system. I mean, this happened overnight. 6 months ago, this team didn't even exist. And so creating such a system takes a lot of infrastructure, and CCIT was instrumental in doing this. We have also a great team of people at Nokia, Rutgers, and ITS. And to finish our, and we have also amazing support from the civil engineering department. Most of the students who are monitoring and regulating traffic, talking to the cars on the phone, helping them, are most of them civil engineering students who have been recruited at the ASC organization, and they have just done a superb job, and it's really a pleasure to work with them. So to finish with a couple pictures so you see what happened today, this is the labels that we put on the car. This is 10 or 20 of the 195 phones that we've been using. Caltrans was on site yesterday helping us putting tags on the cars, and it was really fun to park 100 cars, and Lowe's were totally terrorized to see what are these Berkeley people doing circling our parking lot and sticking stickers on cars. People were asking, is this going to be a car auction tomorrow? And actually it wasn't. So this was at 7 o'clock in the morning. Now we have all the cars lined up behind. This is my student Dan Work and my student Andrew Tinka, who are finalizing the last bits of details of the logistics. So these are the keys of the cars. Now a bit later at 7:15 the TV comes in, and we're setting all the cones to have good traffic and organization there. Here's the students arrived around 9 o'clock, so we had a lounge so that the students can take breaks during the driving loops. And now at, as I said, early on in the loops, some accident happened and we captured it. The officials from Caltrans arrived fairly soon. And before we knew it, we were running. In fact, this is one of the crew operating from one of the bridges earlier today. This is Bob Iannucci, the CTO of Nokia, who came in for the day just to see this happen. Actually, he wanted to get a helicopter to film it from the top, but we were not ready on time. We had a very nice press conference and a ribbon-cutting ceremony to release the first wave of cars. Finally, I would like to dedicate this talk to my father, who should have been here today. who was a cryptography professor and was very interested in this. He died a month ago, day for day. And this is the last picture of him alive, and he was taken with this N95 phone. And with this, I will leave you with some of the videos of the experiment that we did before, and I will be happy to take any questions.
Excellent. That was fantastic. I think everybody had a wonderful, enjoyable time. Thank you. So let's take a couple of quick questions. It's 5 o'clock. I know people are rushing home, but a couple of quick questions. There's a microphone at the back and one at the front here.
Praveen.
Alex, two questions. A, what exactly is the data that you get from the cell phones? And B, will you make all these data available, like PEMS does and everybody else does?
Okay, so what is the data we get available? Each of the GPS phones here provides speed and position at a 1/3 of a hertz rate. That means every 3 seconds you can know where you are and how fast you're going within GPS accuracy. Second question that Praveen asked is, will we make that data available? So for this specific experiment, there's an NDA that we have put together with Nokia, so there is a plan of doing this. Now, if you're asking more in a business perspective, I think our vision is really, we would like to have a PEMS similar system for this. And I don't want to go ahead too much, but our next operation is probably going to be 1,000 or 10,000 phones in a very different setting, and we really like to do this real quickly. And having a tool like you have developed for PEMS for this is really on our radar screen.
Another question from the floor? Yeah, hi. Okay. Can you speak in the This is being recorded, so please use the microphone if you can.
There are already some traffic monitoring alert services, like my Garmin provides one using FM transmitter. How different it is? Why are you doing this when there is already one? Is that not accurate enough, or yours is better than theirs?
Well, okay, so I think here you have to keep in mind that what we are interested in here is defining the borders of privacy and accuracy. And I think I'm not familiar exactly with the details of the technologies you are talking about, but there are key points here. A, we're using GPS, and that's a relatively new thing in this community of transportation engineering. And B, we are building an environment which is privacy preserving. And again, so our main emphasis here is the privacy preservation.
Hang on a second. Can you capture this on the microphone for our 3 other campuses?
I was talking in terms of calculating your travel speed, and if you want to reroute your traffic to go through other routes because the traffic is congested, I think Garmin does it by rerouting and alerting you that there is a traffic congestion at certain route.
There's 2 things which should not be confused here. There's the detection and traffic flow reconstruction, and then there's the route advisory. Now, these are totally different things here. Today, we're not showing an algorithm to find the shortest route because we only have one route. That's a totally different problem. Today, what we're doing is we're doing a system that collects data and a new set of data and uses it to produce a product that is helpful for users.
That's a good answer. That's a clear answer. That's good. Another question from the floor? One last question here.
So how are you collecting this data, and how are you storing this data? Is it all stored on the cell phone?
Okay, so to answer to that question, for the day of the experiment, we are storing that data on the phone so that, as Praveen suggested, we have later a database of things that we can use to do further studies. Now, the system that we are putting together does not store the data on the phone. It sends it, it's anonymized, encrypted, and everything, blended in a general stream of data, and that's it. So it's not stored in the phone.
But I could store the data if I wanted to using, what's the process that you're using to store this data?
So there's a memory card. So it's nothing.
So you're writing a script?
Yeah, exactly. There's a client running on the phone, and it basically enables you, if you wanted to, if you wanted to track yourself throughout the day, we can do it. It's very simple.
Okay, great. I'm sometimes lost, so I like to do it. One last clean-up question. I think you got it, right? You beat it just to the second.
I'm not sure if it's clean up or not. So if you're going to deploy the system, you need it, and it's a random number of random drivers who take trips at random times. So what if I wanted to do the East Bay? How many phones do I have to have deployed out there, and how much data are they sending back?
That's a good question.
So I'm sorry, I didn't hear very well.
Oh.
Can you just repeat the question?
Basically, how many phones do you need to have an effective monitor system for, say, the East Bay? And how much data is
Right.
that going to actually consume as they send back data?
Okay, so actually, what we're gonna try to do more. We're not gonna. I think our next move might not be the East Bay, but maybe 101. But okay, a very similar type of setting. We have not done the back of the envelope computations, but I think the ballpark figures are. I think with 1,000 to 10,000 cars and daily commute patterns of user selectors, we're not going to operate in the same mode at all. It's a totally different model because it's more a long-term collection thing. We will be able to provide a very similar level of data.
And with that, I'm sure Alex will stay for a while.
Yeah.
And please come up and ask more questions. And I think that was a wonderful way to end the week before we adjourn to the bar. Let's give him a round of applause. Fantastic. Fantastic. JD, nice job.